Hello there, and welcome to the Slumber Lab, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey explores one of the most fundamental questions in physics. Why can't you go faster than light? It's a question that sounds simple enough, but the answer reveals something profound about the very fabric of reality itself. Before we begin our quiet drift through the cosmos, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the universe. It's rather fitting, isn't it? A video about the speed of light, and here we are, scattered across time zones, each arriving at this moment through our own unique slice of space-time. If you find this voyage soothing, intriguing, or just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little corner of calm reach others who might need a peaceful pause in their evening. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something remarkable about the universe before you drift off. So settle in, slow your thoughts, and let's begin. Because somewhere between photons and physics, between relativity and rest, lies one of the most elegant limits nature has ever imposed. Picture, if you will, a single beam of light drifting through the vast emptiness of space. No planets, no stars, no gravity pulling at it. Just one solitary photon gliding effortlessly through the vacuum, neither speeding up nor slowing down. It moves at exactly 299,792,758 meters per second, and it has no choice in the matter. This isn't just a speed, it's the speed. The cosmic speed limit that governs everything from the smallest particle to the largest galaxy. But why this number? Why not something faster, something more convenient? The answer, as we'll discover, isn't arbitrary at all. It's woven into the very structure of space-time itself, a fundamental constant that keeps the universe ordered, logical, and beautifully consistent. You see, light isn't just photons bouncing around. It's electromagnetic radiation, waves of electric and magnetic fields dancing together in perfect harmony, oscillating at right angles to each other and to their direction of travel. These waves don't need anything to travel through, unlike sound waves that need air, or water waves that need, well, water. Light just goes, racing through the vacuum of space without a care in the world. And here's where it gets interesting. All forms of electromagnetic radiation, from the longest radio waves to the shortest gamma rays, travel at exactly the same speed in a vacuum. Your favorite radio station, the infrared heat from your morning coffee, the visible light streaming through your window, the X-rays at the doctor's office. They're all part of the same electromagnetic spectrum, all racing along at the same relentless pace. This speed, which physicists call c, isn't just fast, it's fundamentally fast. It's not that light chooses to go this speed, it's that this is the only speed massless particles can travel. Light has no rest mass, no substance in the traditional sense. It exists only in motion, always moving, never at rest. If a photon were to somehow stop, it wouldn't just be taking a break. It would cease to exist entirely. But the story of understanding light's speed is as much about human curiosity as it is about physics. For most of history, people assumed light moved instantaneously. You lit a candle, and the room lit up. The sun rose, and the world turned golden. No waiting, no delay. It seemed obvious, really. Then came Galileo, bless his curious heart, who around 1638 tried to measure light speed using lanterns and hilltops. He and his assistant would stand on hills about a mile apart, each with a covered lantern. Galileo would uncover his lantern, and as soon as his assistant saw the light, he would uncover his own. Galileo would then try to measure the time between sending the signal and seeing the return flash. Now, even under the best circumstances, This was wonderfully optimistic. Human reaction time alone is about 1/4 of a second, while light takes less than 1/10,000th of a second to travel a mile. It's like trying to measure the speed of a bullet with a sundial. But you have to admire the effort, the pure human desire to understand the universe around us. The real breakthrough came from an unexpected source, the moons of Jupiter. In 1676, a Danish astronomer named Ole Rømer was tracking the orbit of Io, one of Jupiter's moons, when he noticed something peculiar. Sometimes Io appeared behind Jupiter a little late, other times a bit early. At first glance, this might seem like cosmic bad timekeeping, but Rømer had a brilliant insight. What if it wasn't Io being inconsistent, but us? What if the delay was caused by Earth sometimes being farther from Jupiter, meaning light from Io had farther to travel? And just like that, the idea of light having a measurable, finite speed began to take scientific shape. From these timing discrepancies, Rømer estimated that light took about 22 minutes to cross the diameter of Earth's orbit. Not perfect, but revolutionary. Later experiments refined these measurements. Fizeau in the 1800s used rotating toothed wheels and distant mirrors, spinning the wheel faster and faster until the returning light beam was blocked by a tooth instead of passing through a gap. Foucault improved the technique with rotating mirrors. Michelson, with his incredibly precise measurements, earned the first Nobel Prize awarded to an American. But the real revelation came when James Clerk Maxwell sat down with everything scientists knew about electricity and magnetism and turned it into 4 elegant mathematical equations. When Maxwell combined these equations, something extraordinary emerged. They predicted electromagnetic waves that would naturally travel at a specific speed. When he calculated that speed using known electric and magnetic constants, he got 299,792,458 meters per second. Maxwell was stunned. He'd found a fundamental speed buried deep within the laws of electricity and magnetism, and it matched the measured speed of light. This wasn't coincidence. It was revelation. Light, Maxwell realized, was an electromagnetic wave, and its speed wasn't chosen randomly by the universe. It was dictated by the fundamental structure of reality itself. But the story doesn't end there. It was Albert Einstein who truly revolutionized our understanding of what this speed limit means. In 1905, with his special theory of relativity, Einstein made a bold claim. The speed of light in a vacuum is constant for all observers, no matter how fast they're moving. This might sound innocent enough, but it breaks everything you think you know about motion. In our everyday world, speeds add up. If you're walking on a moving sidewalk, your speed is your walking speed plus the speed of the belt. But with light, this doesn't happen. Whether you're standing still or racing toward a light source at incredible speeds, you always measure that light moving at exactly the same speed. To make this possible, reality has to bend itself around this rule. Time slows down, lengths contract, mass increases. The universe changes the way it ticks to ensure that no one, no matter how fast they go, can ever observe light speeding up or slowing down. And here's where the speed limit becomes absolute. If you tried to accelerate to the speed of light, your mass would increase toward infinity, meaning you'd need infinite energy to reach it. It's not just impractical, it's impossible. 99896% of light speed, but you can never quite get there. This isn't just a quirk of physics. It's a fundamental protection for causality itself. The speed of light ensures that causes happen before effects, that information can't travel into the past, that the universe maintains a logical order. Without this limit, we could theoretically send messages to our past selves, create paradoxes, and watch reality unravel into chaos. Instead, we have a universe with structure, with order, with beautiful consistency. Light doesn't just illuminate our world, it sets the rhythm of spacetime itself. Every GPS satellite, every fiber optic cable, every measurement of distance and time depends on this fundamental constant. Even now, as you listen to these words, you're experiencing the speed of light in countless ways. The photons from your screen travel to your eyes at exactly this speed. If you're using Wi-Fi, electromagnetic waves carry this information through the air at nearly light speed. The very atoms in your body, forged in ancient stars, were once carried across the universe by light itself. The speed of light isn't just a number in a physics textbook. It's the universal translator between space and time, the conversion factor that allows us to measure distances in light years and ensures that equations work the same way whether you're on Earth or orbiting a distant star. It's woven so deeply into the fabric of reality that since 1983, we've defined the meter itself based on how far light travels in a specific fraction of a second. In a universe that can seem vast and strange, filled with dark matter and quantum uncertainty, there's something beautifully fixed about the speed of light. It's a constant you can build your understanding around, because we quite literally do. It's not just the speed of photons racing through space, it's the heartbeat of the cosmos, the steady pulse that keeps reality in rhythm. So tonight, as you drift towards sleep, perhaps you'll think of those photons still racing through the darkness, carrying starlight across impossible distances, moving at the only speed they know how to move. They've been traveling since before Earth existed, and they'll continue long after we're gone, always at the same patient pace, always reliable, always exact. The universe may be vast and mysterious, but it whispers its secrets in the language of light. And light, thankfully, always arrives right on time, at exactly 299th and 792,458 meters per second. Not because it chooses to, but because in this elegant cosmos of ours, some things are simply, beautifully, perfectly constant. Now that we've gently explored what light truly is, let's settle into the story of how humans first tried to catch this mysterious traveler and measure its pace. Picture this: centuries of curious minds, armed with nothing more than lanterns, mirrors, and an almost childlike determination to solve one of the universe's most elusive puzzles. For most of human history, light seemed instantaneous. You lit a candle, and the room brightened immediately. The sun rose, and the world turned golden without delay. It was natural to assume that light simply appeared wherever it was needed, like magic responding to a wish. Even the great philosopher Aristotle, whose ideas had an unfortunate habit of sticking around for centuries, believed light travelled instantaneously. Case closed, curiosity shelved, questions deemed unnecessary. But then came Galileo Galilei, a man who refused to accept things simply because someone important had declared them true. Around 1638, this brilliant Italian decided to poke at the assumption of instantaneous light with what might be the most charmingly optimistic experiment in scientific history. His plan was beautifully simple. He and an assistant would each take a lantern, cover it, and stand on hilltops about a mile apart. Galileo would uncover his lantern first, and as soon as his assistant saw the flash, he would uncover his own. Galileo would then measure the time between sending his signal and seeing the return flash. Now, even under the best circumstances, this experiment was wonderfully ambitious. Human reaction time alone takes about a quarter of a second, while light takes less than a 10,000th of a second to travel a mile. It was rather like trying to measure the speed of a bullet with a sundial. Still, you have to admire the effort, the gentle audacity of two people standing on hills with lanterns, trying to race light itself. Unsurprisingly, Galileo concluded that if light did have a finite speed, It was far too fast for him to measure. Which was absolutely true, but at least the question had been properly asked. Sometimes the most important scientific breakthroughs begin not with answers, but with the courage to wonder. The real breakthrough came a few decades later from an unexpected source: the moons of Jupiter. Ole Rømer, a Danish astronomer working at the Paris Observatory in 1676, was doing something quite routine, tracking the orbit of Io, one of Jupiter's many moons. Io zips around the gas giant like cosmic clockwork, disappearing behind Jupiter and reappearing with predictable regularity. But as Rømer carefully recorded these celestial comings and goings, he noticed something odd. The timings weren't consistent. Sometimes Io appeared a little late. Other times it seemed to be running early. At first glance, this might have seemed like bad timekeeping, but Rømer had a brilliant insight. What if it wasn't Io that was being inconsistent, but us? What if the delay was caused by the fact that Earth was sometimes farther away from Jupiter, and the light from Io simply had farther to travel? It was an elegant thought. Perhaps light, like a messenger carrying news from distant lands, took time to complete its journey. The longer the distance, the longer the delay. From these timing discrepancies, Rømer estimated that it took light about 22 minutes to cross the diameter of Earth's orbit. Not a perfect measurement by modern standards, but revolutionary nonetheless. For the first time, someone had shown that light takes time, not much time, but enough to matter. This discovery opened the floodgates of curiosity. If light had a measurable speed, then perhaps it could be measured more precisely here on Earth. In the early 1800s, a French physicist named Hippolyte Fizeau decided to bring the measurement home with an ingenious contraption involving a beam of light, a rotating toothed wheel, and a mirror placed several miles away. The concept was beautifully mechanical. Light would pass through a gap between the teeth of the spinning wheel, travel to the distant mirror, and bounce back. If the wheel was turning slowly, the returning light would pass through the same gap and be visible. But if the wheel spun faster, the returning light would hit a tooth instead of a gap and be blocked. By adjusting the wheel's speed until the light beam was completely extinguished, Fizeau could calculate exactly how long it took light to make the round trip. Using this method, he measured the speed of light at about 315,000 kilometers per second, not far from our modern value of 299,792,458 meters per second, especially considering he was working with gears, mirrors, and considerable cleverness. It was like building a cosmic stopwatch from bicycle parts and determination. Later, Léon Foucault refined the technique using rotating mirrors instead of toothed wheels, achieving even greater precision. His experiments showed not only that light had a finite speed, but that it actually moved slower in water than in air, a critical clue that light interacts with materials in ways that affect its velocity. But perhaps the most iconic name in this story is Albert Michelson. In the late 1800s, this American physicist took Foucault's mirror method and refined it to an almost obsessive level of accuracy. He used long tunnels, carefully aligned mirrors, and incredibly precise timing to produce results that stunned the scientific world. His dedication to chasing beams of light with mirrors earned him the Nobel Prize in Physics in 1907, making him the first American to receive this honor. Not a bad reward for what essentially amounted to playing cosmic hide-and-seek with photons. Today, our tools have become almost unimaginably sophisticated. We have lasers that can maintain perfect coherence across vast distances, atomic clocks that tick with precision beyond human comprehension, and satellites that can measure distances to within fractions of a millimeter. In fact, since 1983, we've turned the whole measurement process on its head. Instead of measuring the speed of light, we now use it as a standard to measure everything else. The meter itself is now officially defined as the distance light travels in more 299,792,458 of a second in a vacuum. We've made the speed of light our cosmic ruler, the fundamental measuring stick against which all other distances are compared. It's a poetic reversal. Light, once the mystery we chased, has become the standard by which we measure the universe. But perhaps the most beautiful part of this story isn't the sophisticated equipment or the precise measurements. It's the human element, the chain of curiosity that stretches from Galileo's hilltop lanterns to Romer's patient observations of Jupiter's moons, from Fizeau's spinning wheels to Michelson's obsessive precision. Each scientist built upon the work of those who came before, adding their own piece to an ever-growing understanding of light's nature. The speed of light isn't just a number in a textbook. It's proof that even the most fundamental mysteries can yield to patience, creativity, and the gentle persistence of curious minds. So the next time you flip a switch and light fills the room, remember that the simple act connects you to centuries of wonder. Those photons flooding your space are traveling at exactly 299,792,558 meters per second, not because that's a convenient number, but because that's the speed at which the universe itself has decided that information, energy, and light should flow. It's the cosmic speed limit, discovered not through force or haste, but through the quiet dedication of people who simply wanted to know how fast light could go. And remarkably, that speed hasn't changed since the first photon began its journey through space. It's been constant, reliable, and unchanging, like a metronome keeping time for the entire cosmos. Now that we've gently explored the cosmic speed limit and discovered why light moves at exactly 299,792,458 meters per second, let's settle into something equally fascinating, but perhaps even more mysterious. What happens when massive objects approach this universal boundary? Picture, if you will, a spacecraft drifting peacefully through the void, its engines humming quietly, as it accelerates toward velocities that would make even light take notice. As we've learned, light itself has no choice but to travel at this cosmic speed limit because it has no mass to weigh it down. But what about things with substance, with heft, with the kind of mass that keeps your feet planted firmly on the ground? What happens when we try to push matter itself toward the speed of light? The answer, it turns out, reveals one of the most elegant and quietly dramatic principles in all of physics. Let's begin with something wonderfully counterintuitive. In our everyday world, if you want to go faster, you simply apply more force. Push harder on the accelerator, and your car speeds up. Pedal more vigorously, and your bicycle picks up pace. It seems logical that this relationship should continue indefinitely. More energy in, more speed out, like a cosmic vending machine dispensing velocity in exchange for effort. But the universe, as we've discovered, has other plans. As objects with mass approach the speed of light, something extraordinary begins to happen. It's not that they become heavier in the traditional sense, like gaining weight after a particularly indulgent holiday dinner. Instead, their relativistic mass increases, which is physics' way of saying that they become increasingly reluctant to accelerate further. Imagine trying to push a shopping cart that somehow becomes more difficult to move the faster it goes. At first, a gentle shove sends it rolling smoothly down the aisle, but as it picks up speed, it begins to resist your efforts more and more stubbornly. By the time it's moving quite fast, you're pushing with all your might just to add a tiny bit more velocity. This is essentially what happens to massive objects as they approach light speed, except the resistance doesn't come from friction or sticky wheels. It comes from the fundamental structure of space-time itself. The mathematics behind this is surprisingly beautiful. As an object's velocity approaches the speed of light, the energy required to accelerate it further approaches infinity. Not a very large number, not an astronomically huge amount, literally infinite energy. It's as if the universe has installed an impossibly steep energy tax on approaching the cosmic speed limit, making the final approach not just difficult, but fundamentally impossible. This creates what physicists call an asymptotic approach to the speed of light, 9% and so on, but you can never quite reach 100%. It's like trying to count to infinity. No matter how high you go, there's always further to travel. 99% and 100% of light speed requires more energy than exists in the observable universe. Let's make this wonderfully abstract concept a bit more concrete. Consider the humble electron, one of nature's lightest, massive particles. 99999% the speed of light. At these velocities, an electron's relativistic mass becomes thousands of times greater than its rest mass. The energy required to push it just that tiny bit faster, to cross the final gap to light speed, would be enormous beyond comprehension. But here's where the story becomes even more intriguing. While massive particles can never reach the speed of light, they can get close enough to experience some truly remarkable effects. Time dilation becomes dramatically pronounced. 9% light speed experiences time passing about 22 times more slowly than a stationary observer. 99% light speed, this factor jumps to over 70. The faster you go, the more dramatically time stretches, approaching a complete stop as you approach light speed. Length contraction follows a similar pattern. Objects become shorter and shorter in the direction of their motion as they approach the cosmic speed limit. 5% of its original length to a stationary observer. 4% of its original size. The universe itself would appear to flatten in front of the travelers, distances compressing as if space were being squeezed through a cosmic pasta machine. From the perspective of someone aboard such a high-speed vessel, the journey would feel quite different. Time would pass normally inside the spacecraft. Clocks would tick at their usual pace, conversations would flow naturally, and coffee would still take the same amount of time to brew. But the outside universe would appear to speed up dramatically. Stars would seem to whiz by like cosmic fireflies, and what might be a journey of decades to an outside observer could feel like mere months or even weeks to the travelers. This leads us to one of the most poetic consequences of approaching light speed, the practical possibility of traveling vast distances within a human lifetime. While you could never reach a distant star faster than light itself, you could, in principle, experience the journey as taking much less time. 99% light speed, the journey might feel like only about 18 months. Of course, there's a melancholy trade-off here. When these hypothetical travelers returned to Earth, they would find that over 2 centuries had passed. Everyone they knew would be long gone, their world transformed by the passage of time they barely experienced. It's a profound reminder that while the laws of physics might permit such journeys, they come with costs that extend far beyond fuel and engineering challenges. The energy requirements for achieving such speeds are staggering. To accelerate even a small spacecraft to 90% light speed would require energy equivalent to the total annual power consumption of our entire civilization, multiplied many times over. To reach 99% light speed, the energy requirements become truly astronomical. 9% or beyond requires energy on the scale of what entire stars produce over their lifetimes. This is why, despite our dreams of zipping between stars like characters in science fiction, the speed of light remains an effectively insurmountable barrier for anything with mass. We can approach it, dance around its edges, and experience its strange effects, but we cannot cross it. The universe has drawn a line in the cosmic sand, and that line is absolute. Yet there's something deeply satisfying about this limitation. It preserves causality, ensuring that effects follow causes in a logical sequence. It maintains the orderly flow of time and prevents the paradoxes that would arise if we could outrun the very signals that carry information about events. In a way, the speed of light limit isn't just a restriction, it's a feature that keeps the universe comprehensible and stable. Modern particle accelerators give us a front-row seat to these relativistic effects. 9999 5% the speed of light. At these incredible velocities, the proton's relativistic mass increases by a factor of over 7,000. The energy stored in their motion is so great that when they collide, they can create conditions similar to those that existed just moments after the Big Bang itself. These experiments aren't just academic exercises. They help us understand the fundamental nature of matter and energy, probe the deepest laws of physics, and test our theories about how the universe works. Every time we push particles to these extreme speeds, we're conducting experiments in relativity, confirming Einstein's predictions, and exploring the boundaries of what's possible. But perhaps the most beautiful aspect of this cosmic speed limit is how it connects the smallest scales of particle physics to the largest scales of cosmology. The same principles that prevent a proton from exceeding light speed also govern the behavior of matter falling into black holes, the expansion of the universe, and the propagation of gravitational waves across billions of light-years of space. As you drift towards sleep tonight, consider this remarkable fact. While nothing with mass can travel faster than light, the universe itself has found ways to move vast amounts of matter and energy across incredible distances. Cosmic rays, high-energy particles from deep space, regularly strike Earth's atmosphere after traveling for millions or billions of years at speeds very close to light speed. These particles carry messages from distant corners of the universe, stories written in the language of high-energy physics, and delivered at nearly the maximum possible speed. In a sense, we are constantly being visited by matter that has pushed the boundaries of the possible, that has traveled as fast as anything with substance can travel. When these cosmic messengers interact with our atmosphere, they create cascades of secondary particles, brief fireworks displays of relativistic physics happening miles above our heads. So while we may never build starships that approach the speed of light, we live on a planet that is constantly being touched by matter that has made such journeys. The universe, it seems, is always conducting its own experiments with the cosmic speed limit, sending us samples of what's possible when matter dances at the very edge of the ultimate boundary. And perhaps that's enough. Perhaps there's something profound about living in a universe where the fastest possible speed is also the speed at which information and causality can travel, where the cosmic speed limit isn't arbitrary but fundamental, and where the boundary between possible and impossible is written not in human law, but in the very geometry of space-time itself. Welcome back to the Slumber Lab, where cosmic questions get cozy and physics puts on its pajamas. Tonight, we're gently drifting into one of the most fascinating frontiers of Einstein's universe. What happens when you try to outrun light itself? We've discovered that light moves at an absolute speed limit, that this limit shapes the very fabric of space and time, and that nothing with mass can ever quite reach it. But now, let's explore the beautiful and strange consequences of getting close. Picture this. You're aboard a spacecraft, sleek and impossibly advanced, humming quietly through the void. Your destination lies ahead, but you're not in any ordinary hurry. You're attempting something that pushes against the fundamental rules of the cosmos itself. You're trying to approach the speed of light. What would happen? How would reality itself begin to bend around you? The first thing you'd notice, though notice might be too gentle a word, is that acceleration becomes increasingly difficult. It's not like pressing harder on a car's gas pedal and feeling the engine strain. Instead, it's as if the universe itself is becoming reluctant to let you go faster. Your spacecraft's engines, no matter how powerful, would need more and more energy to achieve smaller and smaller increases in speed. This isn't stubbornness from your ship. It's Einstein's relativity showing its hand. As you approach light speed, your relativistic mass increases dramatically. The closer you get to that cosmic speed limit, the more energy you need to accelerate even a tiny bit further. At 90% the speed of light, you'd need roughly twice as much energy to speed up compared to when you started. At 99%, you'd need over 7 times as much. At 99.9%, you'd need over 22 times the energy. The mathematics are elegant but unforgiving. It's like trying to climb an infinitely steep mountain that grows steeper with every step. No matter how much energy you pour into your engines, light speed remains just out of reach, a horizon that recedes as you approach it. But let's imagine your spacecraft somehow has access to tremendous energy reserves. As you accelerate closer and closer to light speed, something extraordinary begins happening to time itself. Your onboard clocks start ticking more slowly compared to the rest of the universe. This isn't a malfunction or an illusion. Time dilation is one of the most well-tested predictions of special relativity, and it becomes increasingly dramatic as your speed increases. At 50% light speed, time aboard your ship would pass about 13% more slowly than for observers back on Earth. Noticeable, but not dramatic. At 90% light speed, your clocks would tick less than half as fast as Earth's. What feels like 1 hour to you would be over 2 hours for everyone else. At 99% light speed, time aboard your ship would crawl to about 1/7 the rate of Earth time. A week-long journey from your perspective might represent nearly 2 months passing on Earth. The mathematics become truly staggering as you approach the speed of light asymptotically. At 99.9% light speed, your time would pass at about 1/22nd the rate of Earth time. A single day aboard your ship would correspond to over 2 months on Earth. At 99.99%, the ratio becomes even more extreme. Your hour becomes nearly 3 Earth days. From your perspective aboard the ship, everything feels perfectly normal. Your coffee still steams at the right temperature. Your heart beats its familiar rhythm. Your watch ticks along steadily. But if you could somehow peer back at Earth, you'd see the planet spinning faster and faster beneath you. Seasons would cycle rapidly. Years would pass in what feels like weeks. The universe around you would appear to be stuck in fast-forward mode. Meanwhile, space itself begins to behave strangely. Length contraction kicks in, though you won't notice it happening to your own ship. From your reference frame, everything aboard feels perfectly normal-sized, but the universe ahead of you starts to compress in the direction of your motion. Distances that once seemed vast begin to shrink. The journey to nearby stars, which would normally take years even at incredible speeds, starts to feel shorter and shorter. This isn't just a visual trick or an optical illusion. Space is genuinely contracting from your perspective. At 90% light speed, distances in your direction of travel would appear to shrink to about 43% of their normal length. That 4 light-year journey to Alpha Centauri would seem like less than 2 light-years. At 99% light speed, distances would contract to about 14% of their rest length. At 99.9%, they'd shrink to less than 5%. The combination of time dilation and length contraction creates one of relativity's most beautiful symmetries. While earthbound observers see your clocks running slow, you experience the journey as taking less time because the distances have contracted. Both perspectives are equally valid. Both are describing the same physical reality from different reference frames. The universe maintains its consistency by allowing space and time to flex in perfect coordination. But there's another effect that becomes increasingly noticeable as you approach light speed. The Doppler effect for light itself. Light coming toward you from ahead would appear increasingly blue-shifted, gaining energy and frequency. Light from behind would appear red-shifted, losing energy and stretching toward longer wavelengths. At extremely high speeds, visible light from ahead might shift into dangerous ultraviolet or even X-ray wavelengths, while light from behind could redshift into infrared or radio waves. The universe around you would begin to look increasingly strange. Stars ahead would appear brighter and bluer, packed with high-energy radiation. Stars behind would fade, and redden. The cosmic microwave background radiation, that gentle afterglow of the Big Bang, would become dramatically blue-shifted in front of you. What started as cool microwave radiation might transform into scorching gamma rays. Your spacecraft would need incredible shielding to protect against this cosmic radiation bath. There's also a visual effect called relativistic beaming. As you approach light speed, your forward view would compress into an increasingly narrow cone. Light from all around you would appear to come from directly ahead, creating a tunnel vision effect. The universe behind you would seem to disappear into darkness, while everything ahead would be compressed into a bright, energetic spotlight. It would be like driving through a tunnel where the opening ahead gets smaller and brighter, while everything else fades to black. The energy requirements for maintaining such speeds are genuinely astronomical. The kinetic energy of an object approaching light speed grows without bound. A spacecraft with the mass of a small car traveling at 99.9% light speed would have kinetic energy equivalent to all the electricity generated by human civilization in several years. The faster you go, the more dramatic this energy requirement becomes. This is why particle accelerators, despite being among the most powerful machines humans have ever built, can only accelerate tiny subatomic particles to near-light speeds. Even then, the energies involved are enormous. The Large Hadron Collider can accelerate protons to 99.9999% the speed of light, but each proton carries only the kinetic energy of a flying mosquito. Scaling that up to something as massive as a spacecraft would require energy sources beyond our current technological imagination. Yet even if we somehow solved the energy problem, other challenges would emerge. The interstellar medium, that thin soup of gas and dust between stars, would become a significant hazard. At normal speeds, these sparse particles pose no threat, but at near-light speeds, even individual hydrogen atoms would strike your spacecraft with the energy of cosmic rays. A single proton impact at 99.9% light speed would carry about as much kinetic energy as a grain of sand dropped from shoulder height. That might not sound like much, but when millions of such impacts occur every second, the cumulative effect would be like flying through a sandstorm of high-energy particles. The radiation from these impacts would be intense. Your spacecraft would glow with Cherenkov radiation as charged particles moved through its hull faster than light can travel through matter. The entire ship would become a cosmic lighthouse, blazing with blue light as relativistic particles interacted with its structure. Any biological crew would need extraordinary radiation shielding, adding mass and complexity to an already challenging engineering problem. Navigation, too, becomes increasingly difficult at relativistic speeds. The time it takes for signals to travel between your ship and Earth grows problematic. At half-light speed, a radio signal from Earth would take twice as long to reach you as it would take you to travel the distance the signal covers. Communication becomes delayed and difficult. Course corrections must be planned far in advance. Real-time control from Earth becomes impossible. Even more fundamentally, the relativistic effects would make navigation challenging. Your measurements of distance and time would differ dramatically from those made by Earth-based observers. Star positions would appear shifted due to relativistic aberration. The entire stellar map would look distorted from your high-speed reference frame. GPS satellites, assuming they could somehow track you at such speeds, would need to account for both special and general relativistic effects on a scale far beyond current systems. Perhaps most remarkably, there's a theoretical limit to how close you can practically get to light speed, even with unlimited energy. As you approach the speed of light, quantum effects begin to play a role. The uncertainty principle suggests that confining particles to smaller and smaller regions of space requires more and more energy. At some point, the energy density becomes so extreme that it might create black holes or trigger other exotic quantum phenomena. Some physicists speculate about a practical speed limit, slightly below the speed of light, beyond which the physics becomes so extreme that even theoretical spacecraft couldn't survive. This isn't a hard barrier written in the laws of physics, but rather a practical limit imposed by the increasing hostility of the universe at such extreme speeds. Yet despite all these challenges, the journey toward light speed reveals something profound about the nature of reality. It shows us that space and time aren't fixed backgrounds against which events unfold, but dynamic aspects of the cosmos that respond to motion and energy. It demonstrates that the speed of light isn't just fast. It's the speed at which causality itself propagates through the universe. The closer you get to light speed, the more you begin to experience the universe as light itself does. For a photon, traveling from one edge of the observable universe to the other takes no time at all. From light's perspective, if we can call it that, emission and absorption happen simultaneously. The photon exists only in the act of motion, never at rest, never aging, never experiencing the passage of time. This offers a strange kind of cosmic perspective. As you approach light speed, you begin to touch something like eternity. Your subjective time slows to a crawl compared to the universe around you. You could theoretically witness the far future of the cosmos, watching stars form and die, galaxies collide and merge, perhaps even the heat death of the universe itself, all while experiencing only a brief moment of proper time. It's a reminder that speed isn't just about getting from one place to another quickly. At relativistic velocities, speed becomes a way of traveling through time itself. The universe's speed limit isn't just a rule about motion, it's a fundamental feature of how reality is structured, how space and time interweave, and how the cosmos maintains its elegant consistency. So while we may never build spacecraft that approach the speed of light, the journey toward that limit teaches us something essential about our universe. It shows us that the cosmos is far stranger and more beautiful than everyday experience suggests. It reveals that time and space are not immutable, that the speed of light is not just a velocity but a cosmic principle, and that the universe has built-in safeguards to preserve causality and logic. The speed of light remains our cosmic horizon, unreachable but eternally present, shaping everything from the smallest quantum interactions to the largest structures in space. And perhaps that's exactly as it should be. So far in our exploration of light's fundamental speed limit, we've journeyed through the historical quest to measure this cosmic constant, unraveled how Einstein's relativity makes this speed absolute and inviolable, and seen how the universe itself bends around this sacred number. We've discovered that nothing with mass can reach light speed due to infinite energy requirements, and we've witnessed how this limit preserves causality and gives structure to space-time itself. But now, as we drift deeper into this cosmic mystery, let's gently explore what happens when objects approach this ultimate boundary. Picture yourself floating peacefully in a spacecraft, drifting through the void at what feels like a reasonable pace. But as your ship's engines fire and you begin to accelerate toward ever higher velocities, something extraordinary starts to happen. The universe around you begins to transform, not through magic or imagination, but through the fundamental laws of physics themselves. This is where our journey takes us into the realm of relativistic effects, those strange and beautiful consequences that emerge when matter dares to chase the speed of light. Let's begin with time dilation, perhaps the most poetic of all relativistic phenomena. As your spacecraft accelerates to higher and higher fractions of light speed, time itself begins to stretch and slow. Not just your perception of time, but time itself, measured by the ticking of atomic clocks, the decay of particles, the very heartbeat of reality. At 50% the speed of light, time aboard your ship runs about 15% slower than for observers back on Earth. At 90% light speed, time crawls to less than half its normal pace. And as you approach 99% of light speed, each hour that passes for you becomes more than 7 hours for the rest of the universe. This isn't science fiction or philosophical speculation. It's been measured, tested, and confirmed countless times. Particles in accelerators experience this time dilation. GPS satellites must account for it. Muons created in Earth's upper atmosphere live far longer than they should precisely because they're moving at near light speeds. Time dilation is as real as gravity, as fundamental as the rotation of planets. But time isn't the only dimension that bends. Space itself contracts in the direction of motion, a phenomenon called length contraction. As you accelerate toward light speed, your spacecraft literally becomes shorter in the direction it's traveling. Not crushed or compressed, but fundamentally contracted through the geometry of spacetime itself. To observers watching from Earth, your ship appears to shrink, becoming thinner and thinner as it approaches the cosmic speed limit. At 99% light speed, your vessel would appear to be only about 14% of its original length. From your perspective inside the ship, however, everything feels perfectly normal. Your ship doesn't feel contracted, and time doesn't feel slow. Instead, it's the universe outside that appears contracted in the direction of your motion. Stars and galaxies ahead of you seem compressed, while the space you've left behind appears stretched. This reciprocal nature of relativity means that motion is always relative, always a matter of perspective, yet always consistent with the laws of physics. Then there's the Doppler effect, but magnified and transformed by relativistic speeds. Light from objects ahead of you shifts dramatically toward higher frequencies, becoming bluer and more energetic. Light from behind shifts toward lower frequencies, reddening and dimming. At extreme speeds, visible light from stars ahead would shift into dangerous ultraviolet and X-ray radiation, while stars behind would fade into invisible infrared whispers. But perhaps most dramatically, as you approach light speed, your mass effectively increases. Not that you gain material, but that your energy content grows, and energy and mass are intimately related through Einstein's famous equation. The faster you go, the more energy it takes to accelerate further. At 90% light speed, it takes more than twice as much energy to increase your velocity by a given amount. At 99%, it takes more than 7 times as much. And as you approach 100% of light speed, the energy required approaches infinity. This is the mathematical heart of why nothing with mass can reach light speed. It's not just impractical or expensive, it's fundamentally impossible. The universe itself says no, requiring infinite energy for the final push to light speed. 99% of light speed. But that final gap, however small, demands infinite energy to cross. Modern particle accelerators demonstrate this principle beautifully. 9999991% the speed of light, an almost incomprehensible velocity. Yet even with all that energy, even with the most powerful machines humanity has ever built, we can't quite reach that final barrier. The protons get closer and closer, requiring more and more energy for each tiny increment of additional speed. There's something almost melancholic about this cosmic speed limit. It means that even with perfect technology, even with unlimited energy, we could never quite catch a beam of light. We could chase it across the galaxy, across the universe, getting closer and closer, but never quite arriving. Light will always maintain that final, unbridgeable gap, racing ahead at its constant, inviolable pace. Yet there's also something beautiful about these relativistic effects. They show us that the universe is far stranger and more elegant than our everyday experience suggests. Time and space aren't fixed backdrops, but flexible dimensions that bend and flow around motion and energy. The cosmic speed limit isn't just a rule, it's a feature of reality that gives structure to existence itself. As you drift towards sleep tonight, imagine yourself on that relativistic journey, watching the universe transform around you as you approach the speed of light. Time slowing, space contracting, light shifting to new colors, the very fabric of reality revealing its hidden flexibility. And remember that even in this strange realm of near-light speeds, the laws of physics remain consistent, beautiful, and eternal. The speed of light stands as both a limit and a promise, a boundary that defines what's possible while revealing the infinite creativity of the cosmos. In trying to reach it, we discover not just the rules of the universe, but its poetry. We've explored light's nature, measured its constancy, and discovered why it has an unwavering limit. Now let's gently drift into what might be the most profound realization of all. This cosmic speed limit isn't just a rule for light to follow. It's the universe's way of keeping reality itself from unraveling. Picture this for a moment. You're sitting in your favorite chair, perhaps with a warm cup of tea, watching the evening light fade through your window. What you're witnessing isn't just photons bouncing off objects and entering your eyes. You're seeing the fundamental architecture of space-time itself in action. Every beam of sunlight, every glimmer from a distant star, every gentle glow from your reading lamp is following the same universal law that holds the cosmos together. The speed of light, you see, isn't really about light at all. It's about information. It's about causality. It's about the delicate thread that connects cause to effect, ensuring that events happen in a logical order across the vast expanse of the universe. Without this limit, the very concept of before and after would collapse into meaningless chaos. Think of it this way. When you flip a light switch, the electrical signal travels through the wires at nearly the speed of light. When your phone connects to a cell tower, electromagnetic waves carry your message at exactly this cosmic speed limit. When you look at the moon, you're seeing it as it was about 1 1/3 seconds ago, because that's how long it takes light to make the journey from there to your eyes. This delay, this gentle buffer between events, is what keeps the universe orderly. It's what prevents paradoxes from tearing apart the fabric of reality. If information could travel instantly, if there were no speed limit at all, you could theoretically send a message to your past self. You could cause events before their causes. The logical structure that underlies everything we know would simply cease to exist. But there's something even more beautiful happening here. The speed of light doesn't just prevent chaos, it enables connection. Every photon that reaches your eyes has traveled, perhaps for millions of years, to tell you a story. The light from distant galaxies carries information about the early universe, about the birth of stars, about worlds we'll never visit, but can still, in a sense, touch through the gentle medium of light. And here's where it gets wonderfully strange. According to Einstein's theories, space and time aren't separate things. They're woven together into a single fabric called spacetime. The speed of light is the conversion rate between these two dimensions, the universal translator that allows space to become time and time to become space. When you move very fast, time slows down. When you're near something massive, both space and time bend around it. The speed of light is the constant that makes all these transformations possible while keeping the universe coherent. This cosmic speed limit also gives the universe its texture, its depth, its sense of scale. If light traveled infinitely fast, the universe would feel flat, immediate, without mystery. Instead, we live in a cosmos where distance equals delay, where looking farther away means looking further back in time. When astronomers point their telescopes at distant galaxies, they're not just seeing across space, they're seeing across time, watching the universe as it was billions of years ago. There's a quiet poetry in this. The light from the most distant observable galaxies began its journey when the universe was young, when the first stars were just beginning to shine. That ancient light has been traveling through the expanding cosmos for over 13 billion years, carrying with it the image of a universe very different from the one we know today. And tonight, some of those photons will gently touch the mirrors of our telescopes, whispering their ancient stories into our instruments and ultimately into our understanding. This is why the speed of light matters so deeply. It's not just a number in a physics textbook, it's the rhythm of reality itself, the beat that keeps the cosmic dance in time. It ensures that effects follow causes, that the future remains unknowable, that the past stays fixed. It gives structure to space-time and meaning to the concept of now. Even in your daily life, this cosmic constant is quietly at work. The GPS in your car relies on the constancy of light speed to pinpoint your location. The internet depends on it to carry information around the globe. Your eyes use it to see, your phone uses it to communicate, and your microwave uses it to heat your dinner. The speed of light isn't just some distant cosmic phenomenon, it's woven into the fabric of modern life. But perhaps most remarkably, this universal speed limit connects you to everything else. The same physical law that governs the light from your reading lamp also governs the radiation from quasars billions of light years away. The photons bouncing off these words and into your eyes follow the same rules as the light from the very first stars. In a universe that can sometimes feel vast and impersonal, the speed of light reminds us that we're all part of the same cosmic story, all following the same fundamental script. So as you continue through your day, as you watch sunlight stream through windows or stars twinkle in the evening sky, remember that you're witnessing something profound. You're seeing the universe's way of keeping itself sane, of maintaining order in the face of infinite possibility. The speed of light isn't a limitation, it's a liberation. It's what allows the cosmos to be comprehensible, predictable, and ultimately beautiful. And there's something deeply comforting in that, isn't there? In a world that often feels chaotic and uncertain, it's reassuring to know that at the deepest level, the universe operates by rules that are both elegant and unchanging. The speed of light has been the same since the first moment of creation, and it will remain the same until the last star fades. It's a constant in a cosmos of change, a steady heartbeat in the vast symphony of existence. Tonight, when you look up at the night sky, you'll be seeing light that has travelled unimaginable distances to reach you, all of it moving at exactly the same speed, all of it carrying stories from the far reaches of space and time. And in that gentle shower of ancient photons, you'll be witnessing one of the universe's most fundamental truths, that there are limits, yes, but within those limits lies infinite wonder. The speed of light isn't just the fastest thing in the universe. So far, we've explored how light itself moves through the universe, but what happens when we step back and look at what light's speed limit actually means for the fabric of reality itself? Because the speed of light isn't just a property of photons or electromagnetic waves, it's woven into the very geometry of space-time, creating boundaries around what can influence what and when. This cosmic speed limit gives the universe its structure, its logic, its sense of order. Without it, cause and effect would become meaningless. Time would lose its direction, and the very notion of before and after would collapse into chaos. The speed of light, in other words, is what keeps the universe comprehensible. Let's begin with something that sounds almost mystical, but is deeply grounded in physics: the light cone. Imagine you're standing in a field and you strike a match. That tiny flame sends light racing outward in all directions at exactly 299,792,458 meters per second. Now picture this light expanding as a sphere, growing larger with each passing moment. The surface of that expanding sphere represents the furthest anything can be immediately influenced by your match. If someone is standing far enough away, say 100 light years distant, they won't even know you lit that match for a full century. From their perspective, your action doesn't exist yet. It's not just that they can't see it. It's that no information, no signal, no influence from that event can reach them until light has had time to make the journey. This creates what physicists call your light cone, a geometric way of mapping out which parts of space-time are connected by cause and effect. Everything within your past light cone could have influenced your present moment. Everything within your future light cone could potentially be influenced by what you do right now. But anything outside those cones, it might as well exist in a completely separate universe. This isn't just an abstract concept. It shapes everything about how we understand the cosmos. When you look up at the night sky, you're not seeing the stars as they are. You're seeing them as they were when their light began its journey to your eyes. The nearest star system, Alpha Centauri, appears to you as it was over 4 years ago. The Andromeda Galaxy shows itself as it existed more than 2 million years ago, when early humans were just learning to use tools. Look deeper into space with a telescope, and you're essentially building a time machine. The most distant galaxies we can observe appear to us as they were billions of years ago, when the universe was young and our own solar system didn't even exist. The light from those ancient galaxies has been traveling through space longer than Earth has been a planet, carrying messages from an era we can never visit, except through these patient photons. This delay isn't just a curiosity for astronomers. It's a fundamental feature of reality that prevents paradoxes and keeps the universe logically consistent. Because information can't travel faster than light, you can't influence your own past. You can't send a message to yourself yesterday, warning about the mistake you're about to make. The speed of light acts as a cosmic firewall, protecting causality from the kinds of logical loops that would tear reality apart. Think about it this way. If you could somehow send information faster than light, you could use the relativity of simultaneity, the fact that now is different for observers moving at different speeds, to create a scenario where effect precedes cause. You could receive a reply to a message before you sent it. You could be warned about an accident and prevent it, which would mean there was no accident to warn you about in the first place. The universe would become a contradiction. Instead, the speed of light ensures that causes always precede their effects, that information flows in an orderly fashion from past to future, and that the story of the universe unfolds in a way that makes sense. It's not just a speed limit, it's the universe's way of maintaining its own logical consistency. This principle shows up in the most practical aspects of modern life. When you make a phone call to someone on the other side of the planet, there's a tiny but measurable delay as your voice, converted to electromagnetic signals, travels at light speed through cables and satellites. If you're talking to someone via satellite internet, you might notice a slight pause in the conversation. That's light speed at work, creating a brief moment of silence as your words journey through space and back. For spacecraft exploring other planets, this delay becomes much more significant. When mission controllers on Earth send commands to a Mars rover, it can take anywhere from 4 to 20 minutes for those signals to arrive, depending on where Earth and Mars are in their orbits. There's no real-time remote control across interplanetary distances. The rover has to be smart enough to make decisions on its own, because by the time Earth receives a signal that something's gone wrong, it might be too late to help. Even your favorite streaming service operates within these constraints. Every pixel of every frame in your late-night documentary binge had to travel from servers through fiber optic cables, moving as pulses of light at the maximum speed the universe allows. The infrastructure of the internet itself is limited by how quickly light can move through glass and along wires. But perhaps the most profound implication of light's speed limit is how it shapes our understanding of time itself. Einstein showed us that there's no universal now, no cosmic clock ticking simultaneously everywhere in the universe. Instead, every observer has their own local time, their own personal now, and these can differ depending on motion and gravity. The speed of light doesn't just limit how fast things can move through space, it fundamentally defines the relationship between space and time. In Einstein's equations, space and time are woven together into a single fabric called spacetime, and the speed of light is the conversion factor between spatial distances and temporal durations. It tells us how much space is equivalent to how much time. This is why we can measure distances in light years. A light year isn't a unit of time. It's a unit of distance, specifically the distance light travels in 1 year. The fact that we can use a time-based unit to describe space reveals how deeply interconnected these dimensions really are. The speed of light is the thread that weaves space and time into one unified tapestry. In this view, the universe isn't just a collection of objects moving through empty space. It's a dynamic, evolving geometry where the very fabric of reality can stretch, bend, and curve. Massive objects like stars and black holes warp this fabric, creating what we experience as gravity. And through it all, the speed of light remains constant, serving as the universal measuring stick that gives structure to this cosmic geometry. The speed of light also gives us perspective, literally. Every moment you experience is shaped by how quickly information can reach you. Your perception of now is really a compilation of signals that have traveled to your senses at various speeds. The sound of a friend's voice reaches your ears at a leisurely 343 meters per second. But the sight of their face arrives at light speed, nearly 1,000,000 times faster. Your brain stitches these signals together into a coherent present moment. But that moment is really constructed from messages sent at different times. On cosmic scales, this effect becomes even more pronounced. Astronomers studying distant supernovas sometimes observe the explosion first in visible light, then later in neutrinos that were produced at the same moment, but traveled through space at slightly different speeds. Different types of radiation from the same event can arrive at Earth minutes, hours, or even days apart, each carrying its own piece of the story. The speed of light doesn't just govern what we can observe, it determines what kinds of universe are even possible. In a universe where information could travel infinitely fast, the night sky would be blazingly bright, illuminated by light from every star that has ever existed. The cosmic microwave background, that faint afterglow of the Big Bang, wouldn't exist as a separate phenomenon because all radiation would reach us instantly. Instead, we live in a universe with a built-in speed limit, and that limit creates structure, creates delay, creates the very possibility of change and evolution. Stars can be born and die in distant galaxies without immediately affecting us. Light can travel for billions of years, carrying stories from the ancient universe. Information can flow in an orderly fashion, from causes to effects, maintaining the logical framework that makes science possible. Perhaps most beautifully, the speed of light connects us to the cosmos in a profound way. The photons hitting your eyes right now have journeyed across space and time to reach you. Some left their stars years ago, some centuries ago, some millennia ago. When you look at the night sky, you're not just seeing distant suns, you're receiving messages that have been traveling towards you since before you were born, since before your parents were born, since before human civilization began. The speed of light isn't just fast, it's patient. It gives the universe time to breathe, time to evolve, time to tell its story. And in doing so, it ensures that the universe remains not just a collection of objects, but a coherent narrative unfolding across space and time, connected by the gentle, steady flow of light itself. So the next time you flip a switch and light fills the room, remember that you're witnessing more than just illumination. Now, imagine for a moment that you're floating peacefully in a spacecraft, drifting through the cosmic void at an unimaginable speed. You're traveling at 99% the speed of light, watching distant galaxies blur past your window like streetlights on a midnight highway. The universe stretches and contracts around you in ways that would make Einstein smile with quiet satisfaction. Your journey has been long. Your engines have been burning for what feels like eternities. And yet that final 1%, that last sliver of cosmic velocity, remains tantalizingly out of reach. No matter how much energy you pour into your engines, no matter how desperately you push against the fundamental fabric of reality itself, you simply cannot cross that invisible barrier. This isn't a failure of engineering or imagination. What you're experiencing is one of the most profound and beautiful limitations built into the very bones of existence, the infinite energy barrier. It's the cosmic speed limit's most elegant enforcement mechanism, and it reveals something extraordinary about the relationship between mass, energy, and the speed of light. As any object with mass approaches light speed, something remarkable and slightly unsettling begins to happen. The faster you go, the more energy you need to go, just a little bit faster. But this isn't a linear relationship, like filling up your car's gas tank. This is something far more dramatic, far more absolute. Let's drift gently into the mathematics of this cosmic constraint, shall we? Einstein's special relativity gives us an equation that describes how the energy required to accelerate an object changes with velocity. As you approach the speed of light, the energy requirement doesn't just increase, it explodes toward infinity. At 90% light speed, you need significantly more energy than at 50%. At 99%, the energy requirement becomes almost incomprehensible. At 99.9%, you're looking at energy requirements that would make the entire output of our sun seem like a flickering candle flame. And at 100%, the energy required becomes literally infinite. Infinite energy is not just a very large number. It's not something you could achieve by building bigger fusion reactors or more efficient solar panels. Infinite energy is a mathematical impossibility, a cosmic does not compute that the universe uses to protect the speed of light barrier. Even if you could somehow harness the energy of every star in every galaxy, it still wouldn't be enough. Even if you could tap into the quantum vacuum itself, drawing power from the very structure of spacetime, you would still fall short. The mathematics is unforgiving and absolute. But why does this happen? What is it about approaching light speed that makes energy requirements spiral into infinity? The answer lies in something called relativistic mass, though modern physicists prefer to think of it in terms of relativistic momentum. As an object accelerates, its resistance to further acceleration increases. It's as if the object becomes more stubborn, more reluctant to change its velocity. This isn't because the object is gaining actual mass in the traditional sense, but rather because the relationship between energy and motion becomes increasingly complex as you approach the cosmic speed limit. Think of it like trying to push a boulder up an increasingly steep hill. At first, when you're moving slowly, each push moves the boulder a reasonable distance. But as the hill becomes steeper and steeper, each push accomplishes less and less. Near the top of an infinitely steep hill, you could push with the force of 1,000 titans and barely move the boulder at all. The speed of light represents the top of this infinitely steep energy hill. a summit that can be approached but never reached. This energy barrier has profound implications for how we understand the universe and our place within it. It means that no matter how advanced our technology becomes, no matter how clever our engineering, we will never build a spaceship that travels faster than light. We can get close, tantalizingly close, but that final barrier will always remain. It's not a challenge to be overcome through better science or more powerful engines. It's a fundamental feature of reality itself, as unchangeable as the fact that circles are round or that time moves forward. Modern particle accelerators demonstrate this principle in the most dramatic way possible. 9999991% the speed of light. To achieve this incredible velocity, the LHC uses superconducting magnets cooled to temperatures colder than outer space, thousands of tons of sophisticated equipment, and enough electricity to power a small city. And yet, despite all this technological prowess, despite energies that would have seemed godlike to earlier generations, these protons never quite reach light speed. They approach it asymptotically, getting closer and closer, but never arriving at that final destination. The energy requirements tell the story beautifully. To accelerate a proton from rest to 50% light speed requires a certain amount of energy. To push it from 50% to 90% requires significantly more. To nudge it from 99% to 99.9% requires orders of magnitude more energy still. Each decimal place becomes exponentially more expensive until you're investing cosmic amounts of energy for infinitesimal gains in velocity. It's like trying to count to infinity by adding 1 each time. You can keep going forever, getting larger and larger numbers, but you'll never actually reach your destination. This creates what physicists call an asymptotic approach to light speed. You can get arbitrarily close as you want, but you can never actually get there. It's similar to the mathematical concept of a limit, where a function approaches a value but never quite touches it. In this case, the function is the velocity of a massive object, and the limit is the speed of light. No matter how much energy you add to the system, you're always approaching, but never arriving. The beauty of this cosmic speed limit lies not just in its absoluteness, but in its protective function. If massive objects could exceed light speed, causality itself would break down. We could send information into the past, creating paradoxes that would unravel the logical structure of the universe. The infinite energy barrier isn't just a limitation, it's a safeguard. It protects the universe from logical inconsistency, ensuring that cause always precedes effect, and that the flow of time remains unidirectional. There's something almost poetic about the fact that the universe enforces its speed limit not through cosmic police officers or warning signs, but through the elegant mathematics of energy and motion. It's as if reality itself has been designed with this fundamental constraint built into its very foundation. The speed of light isn't just the maximum velocity, it's the organizing principle around which all of physics revolves. This energy barrier also reveals something profound about the nature of light itself. Photons, the particles of light, have zero rest mass. This means they don't experience the infinite energy barrier that affects massive objects. For photons, traveling at light speed isn't just possible, it's mandatory. They cannot slow down, they cannot speed up, they can only travel at exactly 299,792,458 meters per second. In a sense, photons live on the other side of the infinite energy barrier, in a realm where the rules that govern massive objects simply don't apply. As you float there in your imaginary spacecraft, watching the stars wheel slowly past at 99% light speed, you might feel a sense of cosmic humility. You've pushed against the very limits of what's possible. You've touched the edge of the infinite, and you've discovered that some boundaries are not meant to be crossed. The speed of light stands as a monument to the elegant constraints that make our universe comprehensible, predictable, and beautifully ordered. The infinite energy barrier reminds us that even in our wildest technological dreams, even in our most ambitious science fiction fantasies, we remain subject to the fundamental laws that govern all of existence. We can explore the cosmos. We can journey to distant stars. We can push the boundaries of human knowledge and capability, but we will always do so within the gentle but absolute constraints that the universe has set for us. And perhaps that's exactly as it should be. After all, in a universe without limits, without the elegant mathematics of impossibility, there would be no structure, no order, no reliable foundation upon which to build our understanding of existence itself. So as you drift there in the cosmic dark, your engines finally quiet, your fuel exhausted, you might find yourself grateful for this beautiful limitation. The speed of light isn't just a scientific curiosity tucked away in physics textbooks. It's the invisible conductor orchestrating a symphony that touches every corner of existence. From the ancient photons carrying stories from the edge of the observable universe to the fiber optic cables beneath your feet, delivering this very message. Light speed weaves through reality like a golden thread connecting the vast cosmos to the intimate details of daily life. We've journeyed through the mathematical elegance of Maxwell's equations, where light speed emerges not as an arbitrary number, but as a fundamental constant encoded in the very structure of electromagnetic fields. We've watched Einstein reshape our understanding of space and time, revealing that the speed of light isn't just fast. It's the cosmic speed limit that prevents the universe from descending into causal chaos. This limit ensures that causes precede effects, that time flows forward, and that the logical order of events remains intact across all of space and time. The implications ripple outward in ways both profound and practical. Every GPS satellite orbiting overhead must account for relativistic effects, their atomic clocks adjusted for the time dilation caused by their motion and their position in Earth's gravitational field. Without these corrections, your phone would think you're swimming in the middle of an ocean when you're simply walking to the corner store. The internet itself relies on light racing through fiber optic cables at nearly its maximum speed, carrying conversations, cat videos, and scientific discoveries across continents in the blink of an eye. But perhaps most remarkably, the speed of light serves as our cosmic time machine. When you gaze up at the night sky, you're not seeing the universe as it is. You're witnessing its history unfolding in layers. The light from Alpha Centauri left its source over 4 years ago. The gentle glow from the Andromeda Galaxy began its journey when early humans were just discovering fire. And the cosmic microwave background, that faint whisper of ancient radiation, carries photons that have been traveling for nearly 14 billion years since the universe first became transparent to light. This temporal archaeology reveals the speed of light as more than a barrier. It's a bridge connecting us to the deepest past and the most distant reaches of space. Every telescope becomes a time machine. Every measurement of starlight, a conversation with the cosmos as it was eons ago. The finite speed of light gives us access to the universe's childhood, adolescence, and ongoing maturity, written in the language of electromagnetic radiation. The constancy of light speed also protects the universe from paradox. Without this limit, information could theoretically travel faster than causality allows, creating logical loops where effects could precede their causes. Messages could arrive before they were sent. The orderly progression of time could unravel into chaos. Instead, the universe maintains its dignity through this fundamental speed limit, ensuring that the past remains fixed, the present unfolds logically, and the future remains genuinely unknown until light carries its news to our waiting instruments. In the quantum realm, the speed of light takes on even deeper significance. It appears in Einstein's famous equation E equals mc2, revealing the profound equivalence between mass and energy. This relationship explains why nothing with mass can reach light speed. The energy requirements become infinite as you approach that ultimate velocity. Only massless particles like photons can travel at light speed, and they must always travel at exactly that speed, never faster, never slower. The speed of light also emerges from the geometry of spacetime itself. In Einstein's relativity, space and time aren't separate entities but facets of a unified fabric that can stretch, bend, and curve. The speed of light serves as the conversion factor between space and time, the universal translator that allows meters to become seconds and seconds to become meters. It's the fundamental stitching that holds the fabric of reality together. Modern physics continues to probe the edges of this cosmic speed limit. 9999999%, the speed of light, demonstrating that while you can approach this barrier ever more closely, actually reaching it remains impossible for anything with mass. Quantum entanglement creates instantaneous correlations across vast distances, but these spooky connections cannot transmit usable information faster than light, preserving causality even in the quantum realm. The technological applications seem endless. Fiber optic communications rely on light pulses racing through glass at about 2/3 the speed of light in vacuum. Lasers exploit the precise behavior of photons to create everything from delicate surgical instruments to powerful industrial tools. Radio telescopes capture ancient light to map the structure and evolution of the universe. Even medical imaging depends on various forms of electromagnetic radiation, from X-rays revealing broken bones to MRI machines using radio waves to peer inside living tissue. Looking toward the future, the speed of light will likely remain central to humanity's greatest adventures. Any interstellar journey must reckon with the vast distances between stars and the fundamental limit on how quickly information can travel. Even at light speed, a message to Proxima Centauri takes over 4 years for a round trip. Communication with Mars involves delays of up to 20 minutes each way. These aren't engineering problems to be solved, but fundamental features of the universe's architecture. Yet there's something deeply satisfying about this cosmic speed limit. In a universe that could have been arbitrary and chaotic, we instead find elegant mathematical relationships governing the behavior of light, matter, and energy. The same equations that describe a flashlight beam also govern the dynamics of galaxies. The speed of light connects the smaller scales of quantum mechanics to the larger structures in the cosmos, suggesting a profound underlying unity to the laws of physics. The story of light speed is ultimately a story about connection, how information, energy, and causality flow through the universe at the maximum possible rate. It's about how ancient starlight carries the chemical signatures of distant worlds, how the cosmic microwave background whispers secrets from the universe's infancy, and how every photon that touches your eye has journeyed through space at exactly 792,458 meters per second, never hurrying, never dawdling, but maintaining perfect consistency across all of space and time. This constancy offers a kind of cosmic comfort. In a universe full of change and uncertainty, the speed of light remains steadfast. Whether you're watching a sunset, using GPS navigation, or marveling at images from the James Webb Space Telescope, you're witnessing the same fundamental constant that has governed the flow of information through the cosmos since the first light escaped the primordial darkness. So the next time you see light, whether it's morning sunshine streaming through your window, the gentle glow of your phone screen, or the ancient twinkle of distant stars, remember that you're witnessing one of the universe's most fundamental processes. That light carries within it the story of electromagnetic fields, the geometry of spacetime, and the very structure of causality itself. It moves at the only speed it can, the only speed the universe allows, connecting you to the farthest reaches of space and the deepest depths of time. The speed of light isn't just about how fast photons travel. It's about how the universe maintains its coherence, how information propagates through reality, and how the past, present, and future remain logically connected across the vast expanse of space and time. It's the universe's way of saying that while distances may be enormous and time may stretch across billions of years, there is still an underlying order, a fundamental rhythm that connects all things. And perhaps most beautifully, this cosmic speed limit reminds us that we are not isolated observers in an indifferent universe. Every particle in our bodies was forged in ancient stars, and the light from those stellar furnaces has been traveling through space to reach us across unimaginable distances and eons of time. We are quite literally made of star stuff, connected through the patient journey of light to the deepest reaches of space and time. The speed of light stands as both a limit and a promise, a limit that preserves the logical structure of reality, and a promise that information, energy, and light itself will continue their eternal journey through the cosmos, carrying stories from the past and possibilities for the future, all traveling together at exactly the right speed to keep the universe dancing in perfect, timeless harmony.